Good morning, everyone. Today I'll discuss on convolutional neural network, the basic of convolutional neural network, and that is a part of deep neural network. So a deep neural network have two parts. One is called the recurrent neural network, and another is called this convolutional neural network. So here, before going to the main topic, let's discuss on the few basic steps that where it can be applied and what are the difficulties were there in the previous uh, um, technology, and then why convolutional neural network was introduced and how can it be used. So if we just look uh, the basic problems in computer vision. So computer vision, there are multiple problems lies in computer vision, but if we just pick up the very few interesting problems, one is the image classification problem. That is, to if you are given some image and if you are asked that if you ask to the computer that which type of or what is the object is there, so depend on the you will be given some multiple type of images, and by using these different combinations of that, you can come up with a new totally different type of like face morphing or face warping. So these type of problems can lie over there. So these are the very fundamental computer vision problems. So here if you look that how how does the researcher try to solve this problem. So when we go for detecting any objects, or when we go for trying to find it or localize any objects in an image, then first things we need, that is called features of the of an object. So what are the features can be? So it can be color, it can be texture, so and it can be edges or the contour of the any objects. So how does people used to detect that or to create that features? So there are the multiple existing methods are there, like SARF, that is speed of robust feature, hog, histogram of oriented gradient, scale of scale independent feature transform, that is SIFT. So many are there. So in these different methods the researchers come up with, where they try to get some descriptor of any objects, and they used to give it to some machine learning model, where machine will try to learn from this feature descriptor, and after then it will come up with the result that what type of object it is. So it can be called as, so before hog, for example, in SIFT or in SARF, so it can be kind of, you can call it as a matching. So you will be given some template, and from there you will have your some descriptor of any particular object. So when you will be given some testing image, so from the template, if it is matched, so your template is nothing but your feature descriptor. So if it is matched with the stored descriptor, that is your template, then it will tell you that whether it is exist or not. So there are the problems are there. So there are the multiple methods are there. So each problem has some benefits and have some disadvantages. So like these, first of all, these problems are kind of take some time, means computationally it is heavy. Second of all, when you go for this developing this method, so it is limited, it is application oriented. So for each model or each method, you have to develop this feature descriptor, and then you can compare it with your test image. So these are the pipelines of that. So you'll be given some input image, yours, by using some method you will extract that feature, and you will develop a feature descriptor or feature descriptor. From the feature descriptor, that you will use it for the recognition or for detection. So this is the whole pipeline of that computer vision based methods. Then people try to think that, so what I was telling, that classical CV features definition is domain specific and time constant. assuming. That is the main problems over there. So how people try to solve this problem? So then they used, so neural network is a very old model where people, long back people started to use it. But when people tried to introduce neural network in domain of computer vision, then people started to use the whole image as so if we know about the neural network, so it will have some multiple inputs and there will be multiple number of hidden layers, and based on your application or based on your application, so based on your you can say that what type of classification. So for example, you have 3 classes, so you will consider that I will just want to get whether this is cat, dog, or human or person. So it will have only 3 output neurons, so it will give you some percentage of that for corresponding input image. So how will you give it, or how will you use this neural network to train image, train an image? So for that, what are the problems are there? So here, if we just go for a particular example, I'm just going to this slide, so then I'll go back to the previous slide. So here, what is happening? Suppose you have one input image of just a very small image, that is 68 cross 68 image, and it is a RGB image, so it has 3 channels, so 68 cross 68 cross 3. And if you want to pass it to a neural network for training, then your input feature dimension will become very large. Now think of in our current scenario where we use very large size, large images, where it can be 720 or 720, even it can be larger than this. Then just imagine that what is the feature dimension. So that is huge. So handling this and tackling this huge number of features is very difficult. Not only difficult in terms of the complexity, rather in terms of the time also. So this is the problems lies in neural network. So what can be the solution? Can we do it? Yeah. So can we reduce that number of inputs? So we will use neural network, but can we reduce this number of features? So for that, the solution people have come up with that is called convolutional neural network, and it started in 1998 by first introduced by that is called Lekun, and that is called LayNet. So I will just in the next few slides I will describe those model. So here in 1998, people have come up with the first convolutional neural network model, where it will have multiple convolutional layers along with some pooling layer, where it will do some you can say some kind of encryption of that input sizes, and again the input sizes, and ultimately it will reduce that my problem dimension. Then it will pass to one neural network. So let's see what are the different layers exist in this convolutional neural network. So it has 3 parts. One is called the convolutional layer, second is the pooling layer, and third will be fully connected layer. So I will discuss one by one. First we'll look at the convolutional layer. So what does convolution means? So if we just get to know that what does convolution means, for example, here I have my in the left side I have my given input. I have given one input image, and uh, if you just consider that you are using one kind of a filter. So for example, when you use Sobel or Canny edge detection filter, then we take some small size of filter and we convolute over that input image from the left corner, that is from the 1 to the extreme right position of that image, and we convolute. And what happened? It actually convolute pixel by pixel. So it is nothing but the multiplying and then adding them up, and then we just get what is the type of that filter. Based on that, we get that different type of edges. So edges can be horizontal, it can be vertical, or it can be diagonal. So different type of edges we get. So same things has been applied over here. So instead of applying a single filter here, people have come up with that there will be a stack of filters, so which will be applied on the same input image, and thus will get a collection of my feature output. So that will be called feature map. So let's see how does it work. So for example, here I have 6 cross 6 one input image, and here just this is, you just consider it as a binary image, because for simplicity we are just taking it as a binary image. And then we take 2 filters. one is so if we just look at it, so if we just consider it as a top one, filter one is the diagonal, left diagonal filter, and the filter two we take it as a vertical. So what will happen when we will convolute these filters? So my first filter will give me the diagonal edges exist in this input image, and the filter two will give me the vertical edges exist in this input image. So when you convolute, so how does this operate? So it is a 3x3 filter. So when you are applying filter one, and you just consider it that we are starting from the top left corner, just I told you, as I told you. And what will you do? You will do pixel by pixel operation. So here, for example, in the top left, that is one cross one. And then if we just go through the horizontal way, and then if we go to the shift to the vertical, and if we do the multiplication pixel by pixel and then adding them up, what will happen? Here, first we are doing the dot product. That means just here, as in my input in this 3x3 region, I have only the diagonal 3 1. So it will come up some summation value will be only 3. Then stride. So what is stride? Stride means nothing but how many pixels I am skipping. So here, for example, stride is equal to 1. That means just after 1, I'll just go from the very next pixel. So it will just start from the very next pixel. And again, it will convolute over again 3x3 region. So based on my filter size, here the operation will happen. So again, I'm applying, and thus what will happen if I continue? So before continuing this process, if I just show you that if we put stride is equal to 2, then what will happen? So first I'm starting from here, and I'm just skipping 2 pixels on the right side, and I'm starting from the after 2 pixels. So the same operations will be done, just we are skipping 1 pixel. So what will happen here? When you are using the value of stride, a small value, then my output dimension will increase. And whereas if we increase the value of stride, for example, here stride is equal to 2, then my output feature map size will be reduced compared to stride is equal to 1. So here again we are applying the same thing. So we are striding with value 2, and the same thing is happening. So if we see the pipeline, what is the how does it work? And here we are continuing with this. So filter 1 is applied over this area, this region, this red block, and then we are skipping in the right side with stride is equal to 1. So it is continuing, and thus it is completed over here. So here we are ultimately getting only 4 values out of this 6. So then what will we do? We'll skip down towards the column. So we'll skip to the bottom with 1 pixel, and again we'll continue this process. So this process will be continued, and ultimately what will happen? So my filter one, when I convoluted over this input image, so it has given me one 4x4 output. You can call it matrix. So you can call it as image, but here we call it as a feature map. Okay. So here it will generate one feature map. So for individual filter, it will generate each individual single feature map. So as we are showing here with 2 filters, so here we will have total. So here just I have just shown you that what are the operations are being done. So rest as all as 0. So the things are happening over like this. So if we just move it with the filter 2, and again if we repeat this process, so what will happen? Again the same process will be continued, and thus we'll get again another 4x4 feature map. So thus my 6x6 image will be reduced to the dimension to 4x4, but with 2 4x4 feature map. So total it will be 4x4x2. Okay. So you can consider it as an image, but in actual technical term is feature map. So this is the process. Now, if you consider that how does it operate on the, so as I showed you on the binary image, how does it operate? Now, if we show you on the color image, so here it will have the 3 channels, that is R, G, and B, and same thing will happen. So when you are applying, so for individual color channel it will generate. For example, I have two filters. So what will happen? First filter will be applied on my three different channels, and thus it will come up with the three feature map. And so here, when you are applying this filter 1, so it will generate three feature map. Then again, when you are applying filter 2, again it will generate another three feature map. So total it will be 6. So like that it operates. So for individual channel, it actually does operate, and then it come up with the output feature map. So here now the one question, if we just skim through the past few slides. So here, for example, if we take 10 filters and we are applying on the 6x6x3, that is one color channel, means one color image with 6x6 dimension of 6. And if we apply one 3x3 filter, what will be the total number of parameters? So that is the main thing. So here I'm just showing you the visualization thing, but in practical, how does it means how the operations are being done. So here we know that for individual, if we just consider neural network, here for each neuron we will have one input value, and for each input it will have corresponding one weight. So here the same things happen. Here we are, instead of taking one vector, we are taking one matrix. So this matrix is called one filter, and this filter values actually will be randomly initialized, and then it will try to modify in each iteration to come up with, to give me better result. So here, for example, my filter size is 3x3. So what will be the number of parameters? This number of parameters means what are the total number of weight values will be there. So here we are considering total 3x3x3. That means total 27 parameters I will have. Then we know that in each hidden layer, as in neural network, in each hidden layer we add one bias. So here also same things will apply. One bias value will add along with this. So 27 plus 1, that means total 28 number of total weight value will be there, or parameters will be there. Then how many filters we will have? 10 filters. So total number of parameters will be 28 cross 10, that is 280. So that is the total summary of our past 3 or 4 slides, that how does it operate, or what are the mathematics lies over there. So next thing, I'll show you that what is the pipeline. So first we are taking one input image, and then I have shown you in the arrow, with arrow, that we have put some value, that is F, then S, and then P. So what are these values? And then last I mentioned 10 filters. So 10 filters, now we know that we are applying 10 number of filters on this color image of dimension of 39. So F is denoting my filter size. So whenever we will get this type of image of this convolutional neural network, there, if these values are there, we can easily identify, we can easily figure it out what does this value mean. So F denoting the filter size, that is this 3x3, that because always it will be square matrix, so it is only mention the one value. Then is, we already aware of the stride. So here you can change according to your problem. If you want to reduce your output feature map, the last layer feature map, so you can use higher value of, or larger value of stride. Here we have started from S is equal to 1, and P is another thing, that is called padding. So what happened if you just consider that when you are applying one filter, or starting from 1 cos 1.1, that means from the left top left corner. So and you are applying, you are putting one filter on my input image. So what happened? We generally lost the edges. So if some important information lies in the edges of any input image, as we are applying some filter over there, and if my filter only focusing on the vertical, so you just consider the filters. If we just go back to the here. So if we just go back here, for example, this filter here, you can just consider the on the top of the screen, -1, -1, and -1. So when you are applying on this on my image, and if my input image, if edges are having some important information, so here actually that information will be lost. So to avoid this loss, what we will do, we will pad some values around this image, surrounding this image. So this padding value depends on that what is the size of the filter and how much important information are lies over there in your input image. Based on that, we generally pad up. So you can put it as 0. So then what will happen? My extreme left or the edges now will be taken as my intermediate row or intermediate column. So that information won't be lost. So why we use padding. So what will be the effect of this stride and filters on my output? Let's see what is the formula. So size of feature vector. So that is the formula. I have put it over here. If we just calculate that 39 plus 39 and you are applying one filter of 3 along with padding of 0 and stride of 1, then how do you get this 37 cross 37? Just you put this formula and the value in this formula, that is n plus 2pf 2p minus f by s plus 1. So if you just put this f is equal to 3, s is equal to 1 and p is equal to 0, then you will get automatically this value, that is 37. Again we are applying. So how many convolutional layer you will put, you will stack on each other. Based on that, your output ultimate problem dimension will be, or your feature map dimension will be reduced. So in each layer, actually my problem dimension or my input dimension or feature map, whatever you say, that will be reduced, but it will be increasing number, because in each layer we are applying a bunch of filters. As for example, in this diagram, we have started with 10 filters. So why my output is 37 plus 37 cross 10? That means total 10 number of filters or 10 number of feature maps are there. Then we are applying 20. So here now the problem or the feature map dimension reduced to 17, but it has increased in number. So like that it happens. Ultimately, it reduced to 7 plus 7, and when we find that it is enough small, can be converted or can be passed to a neural network, then we do some flattening that I will discuss in the within next few slides. So if we take the whole CNN, if we try to visualize this whole CNN, we are giving or passing one input image, and it is passing through some layers. So we have already discussed the convolution layer. Then next layer it comes, that is called max pooling or average pooling. So nowadays people don't use average pooling. Rather, when AlexNet or before AlexNet, when LeNet came up with, they used average filtering, but then people have switched to max pooling. So how does max pooling work? Let's see. So here I have applied on my 6 cross 6 input image this filter 1, and I have come up with this feature map. So it is now 4 cross 4. Again, the question is, can we reduce this dimension so that we can give less number of information, or if can we reduce this dimension by fully connected layer, that is my neural network part? Yes, we can do. How? Just by applying this max pooling. So max pooling is a hyperparameter. Max pooling, what will happen based on your so same things for filter 2, how does it operate? So what will happen here, this hyperparameter, as I was telling you. So hyperparameter means you will define that how many or what will be the area from that my feature map that you are focusing on, and from that area you will take only the maximum value. So for example, here as I am showing you that if I take max pooling is nothing but a matrix. So if I take 2 cross 2 and I am just mentioning that I am going to apply max pooling, that means one 2 cross 2 filter or 2 cross 2 region will be cropped from my feature map. So here, for example, on the top left side, I am considering 2 cross 2, and from that, whatever the highest value of the pixels, that only will be taken. So when I am applying just 2 cross 2, then again another 2 cross 2. So ultimately what is happening? From 4 cross 4, one feature map, I am coming up into, or I am scaling it down to 2 cross 2. So that is the beauty of this max pooling layer. So it is not a very mathematically jargon, or means it doesn't have so much mathematics behind that. Very basic or simple idea that you are just taking some information you are choosy about this information, which type of information you will choose, and how will you reduce your feature map, how will you reduce the dimension of the feature map. Based on that, you will choose your max pooling size, and thus you will come up with the reduced dimension. So here, as just to show it, how does it work. So from each area, we are just taking the maximum or the largest pixel value. Thus, it will give me only. So why pooling? It is just not only means subsampling pixels will not change that object. Means even in image processing or in computer vision, we many times we found, or we apply generally, that not all informations are important. So we are generally choosy about the information, which information can we take, or can we reduce that this huge dimension
Abhishek,
to the.
we have another
Yes,
9 minutes left for this session.
okay, sir. Okay, okay, so almost to coming to end. So this is the reason. This is the reason why do we use pooling. So here, as we are subsampling, it is not. We are not losing any information. Rather, we are just reducing the dimension of that dimension of the feature map, and thus it will help us to reduce the computational time. So these are the reason. Now, last layer that I will discuss. So CNN compressor, fully connected network. In so last layer that I started with, that first is my convolutional layer, then max pooling layer. Last one is my fully connected layer. So fully connected layer, nothing but it is just a neural network. So here, what we are doing. So I've just mentioned that, reading it out, that we are reducing the number of connections, then shared weight on the edges, max pooling further reduce the complexity. All these things we have seen. So max pooling, this thing is happening. Then the new image after applying the max pooling, and it has been applied. So here, after max pooling, what we are doing, we are just flattening. Flattening means what we are doing. Here I have my this output. This is my after applying the max pooling, and then we are simply flattening, means we are converting into a matrix into a single vector. So thus we are getting a single vector, which is nothing but, now you can find the similarity with that artificial neural network, where this column vector will be nothing but my input layer of my problem. So it will be given as the input to my fully connected layer, and then the operations will be same things as we do in the feed forward neural network, fully connected network. Same things will apply over here. Thus it will give me, based on my output neurons, it will give me the result. So I'm just skimming through very fast that what are the different classical networks exist. So as I already told you, that linear 5. So why 5? Because it has only 5 layers. After that, it has 2 fully connected layers. So like that it works. And then AlexNet. So what happened in each network, it actually increase the layers, and so sorry for interruption, something happened. Okay, so in each network, what happened, that it started with a very small size or small number of convolution layer, and people have come up with more and more convolution layer to get to do some fine processing and to come up with a better accuracy. So this VGG16, so if you just see the number of parameters are increasing in numbers. So last, I will discuss with you that how does it operate. We will try to visualize the intermediate layers in convolutional neural network. So if I give you the input image, or not, you means to the model, if I give the input image, and what happened. So this is the one kind of visualization that how this CNN works in intermediate layers. So we generally use CNN as a black box. So if we try to visualize that what are the different features we try to extract. So as I told you that we generally try to extract the different type of edges. So these edges generally are extracted in the very first few layers. Within first few layers of convolutional neural network, it try to extract the features, that is the different type of edges. So I am showing you here on that VGG16. So in VGG16, in second layer, I am showing you this is the fourth layer. The top left, the bottom left image is the fourth layer output, and this is showing as the 28th channel. So it has total 64 channel. Channel means nothing but the filters. So I'm counting the filters 1 to 64, and I'm showing you the 28th filters output. So it is giving me some kind of edges of this given airplane. And when I'm going to the depth, so we are finding, if you just look at it, when I'm going to the depth in the network, we found that first few layers act as a collection of various edge detectors. At that stage, activation retain almost all information. As we go deeper, activations become increasingly abstract. So why we can't interpret much more information. So they begin to encode higher level of concepts like wings. Here you can see the wings or the body of the airplane. And the last slide, I will show you that when I'm trying to visualize the all filters in a particular layer, so that is the block 2 conv1. So here actually what they did in VG16, if you just go through the VG16 architecture, so they first put 2-3 convolution layer together, then they applied one max pooling layer, again another bunch of convolution layer followed by one max pooling layer. So here I'm showing you block 2 conv1 means the first convolutional layer, and that is block 2, that means the second convolution layer in the first block. And here it is showing you, so total, if you just look at it, total probably 256 total number of filters are there, and they are showing individual. So each filter is doing the operation on the input image and come up with different type of edges, some vertical edges, some horizontal edges, some diagonal edges. So diagonal also can be 45 degree or other way around. So different type of edges it's trying to extract. So as we go deeper and deeper, so it is going to the from the very basic features to the abstract features, that is kind of a patches or kind of the texture of that object or based on the color, and it is trying to figure it out what are the different type of shapes and all. Like for example, car, here I'm showing you the car. For example, it will try to figure it out the wheels shape and the bonnet shape, all this kind of. So like that, it convolutional neural network work. So I'll stop it here, and so that's all. And if you have any question, thank you, everyone.
Abhishek, can you hear me?
Yes.
So we still have another 2.5 minutes left. So if you have any slide like concluding remarks, you can go ahead with that.
No, I didn't put any kind of, but I can show you one just video that how this.
Yeah, go ahead.
Yeah. Okay. Thank you, sir. So I'll try to show you that when recently I tried to visualize that how intermediate layers work, and we given one video to this VG16, and we come up with different type of. So here, for example, so my screen is still. Okay. So here I am showing you the output of second layer, and filter is 28th filter. So here that will repeat. Here you can see one flight is take off. That video I took, very small duration, only 2 seconds duration. So what is happening? You can see that these edges are being, so all over the image it is trying to extract that different edges. So on the background, if you see that the boost type of things, it is trying to get that vertical edges, or whereas in the front side there are the different type of horizontal, vertical, and all type of edges it is trying to extract. And when we go to the next one, that is the fourth layer. So now we are going to into much more depth. Now you can see, still you can see that what type of, or the contour, or you can say the edges, or you can say the shape of that airplane, still it is, you can visually interpret. Now when you are going into much deeper, that is the ninth, almost you are into the in the middle layer of, so here you can see only some white patches and just it is moving. So as I have shown you before that the where from the airplane is taking off, so that we can see only some white patches around there. This is, we are almost in the end layer, so this is not the last layer, but rather this is the 13th layer of so it has total 17 total convolutional layer, and out of that it is 13th. So here we can see nothing can be interpreted. So as I was telling you that as we are going deeper, activation has become increasingly abstract and it is less visually interpretable. So what can we do? uh, I can see, I don't know whether you can you are able to see, but very less information can be interpreted. So only some very small white patches in the center of this video is just moving with some small scale. So if we try to overlay it on my original image, then we can interpret that which area of this aeroplane are being considered and which activation functions, means which weight values are activated more for this particular filter, that we can interpret. So this is 13th layer and this is the last layer. Just I will show you. So here it is much more means you much more abstract, so nothing can be interpreted. So this is less visually interpretable. So like that it works. So now I think it can be here. If I show you another video that is on the activation fourth layer, and that were it was taxing, one airplane is taxing. So different type of areas you can see the white patches. So that are my point of interest, or that the how the model was trained on which classes. Based on that particular areas, obviously there should be some false positive area. It can falsely activate those areas of that image, but it will try to focus on the areas only where by which images, which type of images it was trained with. So this is the whole story of the convolutional neural network. So as I started with, that it can be applied in different areas in convolution, sorry, in computer vision. So I've shown you that how it can be used as for any kind of application. uh, Later you can use it for the classification. So in classification you can just give it the number of output neurons. Based on that, if it is a binary classification, for example you are trying to classify between cats and dogs, then you can just put two output, means you can use some sigmoid function where it will try to predict based on your input image. It will try to predict which type of image it is. If you go for object detection, then you have to consider object detection a little bit tricky. So there we come up with some regression, bounding box regression, where you have to give the labels. Labels means you have to give the where the object is in the training data, and based on that you can apply different type of methods. So there are multiple models exist, and and it do some different type of regression also, and then it try to predict that which location of this in this image the object is there, and it can be applied in multiple areas. So that is the beauty of the convolutional neural network. So here, after convolutional layer, we are applying max pooling. So max pooling is just to reduce the dimension of my feature map. So as I have shown you that we are first, initially we started with two filters and we are applying on 6x6 one input image. So my filter one has given me this feature map, and what we are doing, we are applying 1 2 cross 2 matrix on my this feature map. So 1 2 cross 2 means we will just take every 2 cross 2 cross 2 region from this feature map, and we'll try to extract max pooling, means we'll take the maximum value out of this region. Okay. So for example, but before that I'll show you that what is the filter 2 did. So filter 2 also generated this feature map, and now we'll show you that if we apply 1 2 cross 2 max pooling, what it will do, it will take 2 cross 2 region on this feature map, and from this 4, so 2 cross 2 means total 4 pixels. So out of these 4 pixels, what is the largest pixel value, that will be considered and that will be taken out. Okay, same things will be applied in this filter too. So when I have total, I applied 2 filters on an input image, that was 6 cross 6, and we came up with 4 cross 4 cross 2, because 2 was the number of filters. Now we are applying 2 cross 2. 2 cross 2 means we are just applying one max pooling of size 2 cross 2. Okay, and it will be applied on across the feature maps that were generated from individual or each filters. So what will happen? For the first filter, what is that feature map? From this feature map, it will extract for each 2 cross 2 region, it will generate or extract the largest value. Thus, it is doing this operation. So ultimately, 4 cross 4 is turning into 2 cross 2. Okay. So when you will take it one single matrix, then it will be 3031. That's all. Same things is happening over here in the right side of the screen. We are applying max pooling, and it came up with another 2 cross 2 matrix. So what is happening? From this 4 cross 4 cross 2, we have reduced or subsampled to 2 cross 2 cross 2. So 4 cross 4 cross 2, if you directly put it into or send it to the neural network, then my input size could be 4 cross 4 cross 2 means 16 into 2, 32. So we had to give 32 number of input neurons. But here what we are doing, we are not reducing the information, we are not losing the information, rather we are subsampling and we are reducing the extra information. And now it is 2 cross 2 cross 2 means total 8 number of inputs in the input, in the fully connected layer, my input dimension will be only 8. So that is the working of max pooling layer. And here I've just described that why pooling, because subsampling pixels will not change that object. As we are seeing here, if we subsample, generally we resize that image. When we do resize means we subsample the pixel, we don't take all the values, rather we choose that area, and from that area we try to get few values, thus we reduce that size of this image. And same things we are doing here. From that feature map, instead of the image, from the feature map we are reducing the dimension. So that is the working of this max pooling layer. Instead of max pooling, another pooling is there, that is called average pooling. So instead of taking the maximum value, you will have to calculate, for example, 2 cross 2. So in this 2 cross 2 region, you will have to calculate the average value of these 4 pixels and you will take it. So that is the only difference in between max pooling and the average pooling. So that is that's all about max